work? Are we good?
Does it run?
Okay. We were scheduled to start at 12. I took great care to time the presentation. The 10 minutes I chose to spare worked out very nicely. So with that, if we're ready, I'd like to begin. First, I'd like to thank Jerry, Peter, and everyone who's helped me all along. Especially like to thank our volunteers, Bill Breidenbach and Tommy, and also our volunteers here today helping with the filming and the setup, Rick and Matt. And so if you have any questions and want to hear their stories afterwards, I'm sure they'll have some interesting stories to tell. Thanks for everyone who helped set up. And I would ask all of your help at the end. We do have someone coming in at 1:30, so if you could each grab something and take it to the Fast Runner Lab on your way back to wherever you go, then we'll clear the room nicely. So with that, are we ready? Let's begin. Let's see, I had a laser pointer. I don't know if that'll show on screen. Well, it'll show there. I can point up and down and left and right. And I have that. Okay, the title of our talk today is Fast Runner, the Roadrunner Model. Some time ago, Jerry asked me to actually develop this Roadrunner model out of the familiar models, like the slit model, the inverted pendulum. So we're going to do that. The subtitle is Visualizing Geometric Stability for Highway Speed Bipedal, and it also works for more legs, but bipedal locomotion design. So the things we're going to see today will give us command of the concepts to just choose the dynamic behavior we want as a matter of design geometry. No control effort at all. And we're going to proceed from there. So now I'm just going to talk to the slides and watch the time. If you have questions, I'll pause briefly, but anything extended we'll save for the end, and we should have plenty of time. So with that, at highway speeds, there is simply no time for traditional control methods to apply. Stability of legged robots at these speeds is accomplished entirely by geometric factors. Control of such systems in this context reduces to throttle and steering when we go non-planar. Reaction forces, ground reaction forces, converge to a meta-center located significantly above the center of gravity to produce attitude, well, that's your posture, and speed stabilization of the running robot. The ground contact cloud, which would pretty much be the tire. The ground contact cloud is constrained to be convergent to the surface of a metacentric sphere in a dynamically valid buoyancy and stability analogy. So you get the idea here. Next. Use of pantographic principles facilitates such convergence as a matter of geometrics. So using the control point here, we can constrain what we want and make the foot do that. Next slide. Convergence of ground contact cloud to metaspheric surface is accomplished by a geometric constraint. So when we're in the neighborhood of the ground contact, we lock the control point of the pantograph onto a geometric constraint attached to the main body. Convergence of GRF to metacenter. Could someone go to the workshop and get the, can someone go get the offset CG thing?
Don't worry about it. We won't see your video.
Okay. Well, we'll get there. If someone can bring it by the time we're there. Okay. Convergence of the ground reaction force to the metacenter is accomplished by forward CG offset torque conversion. And I'll show you what that means. Next slide. Efficiency is achieved by nonlinear elastic relief in a self-stabilizing nonlinear auto-resonance. And we'll talk about that.
So Johnny, these statements, are they things that follow from your model, or are they things that you believe to be true and are trying to show?
I'm going to show you today, and then you decide. We will discuss the optimization that is possible with these principles guiding the design. We will explore simulations and physical demonstrations to achieve command of these design principles to graphically characterize, just by inspection, stability and dimensionless speeds. Our target speed for Fast Runner is to emulate the running ostrich at speeds of 30 miles an hour or more. Cognizance of this material that we'll discuss is crucial and will enable us to achieve far higher speeds, higher than 30 miles an hour and so on, and robustness to disturbances that is just phenomenal. Specific